everyone, it's Justin again, bringing you another lesson on completing the square. In this lesson, we'll be looking further into this method and solve some equations that are a bit more complex. On the cover sheet of your PDF, you had 3 warm-up equations. If you haven't had a chance to work on them yet, pause the video to do that now. Here's the first equation. X squared plus 64 equals 289. This equation looks similar to the ones from the previous lesson. I noticed that the only x is already in a square. We might be tempted to go straight into taking the square root of both sides and then splitting it into the square root of x squared and the square root of 64. However, we cannot split a square root over a sum. A good example that reminds me why we can't do that is the square root of 9 plus 16. Due to the order of operations, I first need to add 9 and 16, which gives me 25. All in all, that's just 5. But if I were to distribute the square root and make it square root of 9 plus the square root of 16, that would be equal to 3 plus 4, which is 7. But the correct answer is 5. In general, the square root of a plus b is not equal to the square root of a plus the square root of b. So let's rewind and think of something we can actually do. I can't take the square root right off the bat because of that plus 64, so what do you think we can do about this? How about we just get rid of it? Let's subtract 64 from both sides. That'll do it. I get x squared equals 225, and then I can take the square roots. Our solutions are x equals plus or minus 15. Now let's take a look at the second equation. 2x squared equals 50. Once again, we want to get the square by itself before taking the square roots. That is 2 multiplying with the x squared, so let's divide both sides by 2. We get x squared equals 25, so x equals plus minus 5. Notice how using some inverse operations like getting rid of that 64 and that 2 helped us isolate what is actually being squared so that we're ready to use the square roots. Here's the third warm-up equation. 3 times x minus 8 squared minus 5 equals 7. I notice that once again, we already have our x in a square. You could say that it already has its square completed. There just happens to be some extra operations attached to it. Based on how we solved the previous 2 equations, how would you approach this one? Pause the video here if you now have a different idea from how you first solved it, and try it out. First, we can get rid of that minus 5 by adding 5 to both sides, which results in 3 times x minus 8 squared equals 12. We also want to get rid of that 3 multiplying with our square, so let's divide both sides by 3. We're now left with x minus 8 squared equals 4. Now we're ready to take our square roots, which give us x minus 8 equals plus or minus 2. We add 8 on both sides, and our solutions become negative 2 plus 8, which is 6, and positive 2 plus 8, which is 10. It's important to note how, in all 3 warm-up equations, it was not necessary to complete the square, since they all had their x's already in squares from the start. There were just a few inverse operations away from being ready to be solved with square roots. Let's take a look at 2 examples of how some cleanup work, like we just did in the warm-up, is sometimes necessary before using the strategies from the last lesson. Our first example is solve 2x squared minus 5x minus 3 equals 0 by completing the square. Why is it that this time we do need to complete the square? The x's in this equation aren't all contained in a square like in the last equations. Therefore, we need to build the square ourselves. Do you notice how this equation is a bit different from the ones we solved by completing the square in the last lesson? All of those had only x squared, but this one has 2x squared. I see you're wondering if you can still complete the square with that 2 in there, Mia. Well, yes we can. If we don't want that 2 there, what can we do about it? Let's get rid of it. Since that 2 is multiplying with the x squared, let's divide both sides by 2. That implies dividing every single term by 2. So we get x squared minus 5 halves x minus 3 halves equals 0. Now it's fraction time. Let's make some side workspace over here to do some operations. To build our square, we need to split the negative 5 halves x in half. Getting half of negative 5 halves is the same as multiplying negative 5 halves by 1 half. How is it that we multiply fractions? Mia, do you remember? Oh, that's right, Mia. To multiply fractions, we multiply numerator with numerator and denominator with denominator. So 1 half times negative 5 halves is negative 5 fourths. We then place those 2 halves in our model, and that negative 3 over 2 is an extra piece there. All these terms together equals 0. Our side length becomes x minus 5 fourths, which means we need to have negative 5 over 4 times negative 5 over 4 in our right bottom box, which is 25 over 16. Now we need to figure out what to add on both sides to get that 25 over 16. Negative 3 over 2 plus what is 25 over 16? I'm blanking out here. If we're having trouble figuring out what number to add here, we could make it easier on ourselves by getting that negative 3 over 2 out of the way. If we had nothing in our right bottom box, then we could just add the entire 25 over 16. So how do we get the negative 3 over 2 out of the way? We can just add 3 over 2 on both sides. Then we'd have x squared minus 5 over 2x equals 3 over 2. Much better. Now I have my right bottom box empty, and I can go straight to adding 25 over 16 on both sides. What can we do to simplify the 3 over 2 plus 25 over 16 we get on the right side? We would need common denominators in order to add these fractions. I could fix that by multiplying 3 over 2 by 8 over 8, which is just another way of saying 1. That way they both have a denominator of 16. We'd get 24 over 16 plus 25 over 16, which is 49 over 16. Now that we have our square complete, pause the video and try to take it from here. Our square becomes x minus 5 fourths squared equals 49 over 16. Then we take the square root of both sides and get plus minus 7 over 4. We add 5 fourths on both sides, and our solutions are negative 7 fourths plus 5 fourths, which is negative 2 fourths, and 7 fourths plus 5 fourths, which is 12 fourths. Simplifying both of those fractions gives us x equals negative 1 half and x equals 3. We did it! On to the last equation. Here's our second and final example. Solve 3x times x plus 12 plus 10 equals 238 by completing the square. This equation looks very different from the other ones we've solved. I don't even see any x's squared, which is necessary if we want to complete the square. Let's see if some of our algebra tools can make this equation look like the ones we know how to solve. Pause the video and think about how we could clean up this equation and prepare it for completing the square. First, we can subtract that 10 on both sides, and we get 228 on the right side. At this moment, we actually have two different approaches we could take. In the first approach, we would first distribute that 3x and get 3x squared plus 36 equals 228. And then, since we need just x squared to complete the square, we divide both sides by 3, and we get x squared plus 12x equals 76. In the second approach, since the 3 in 3x is itself a factor on the left side, we could first divide both sides by 3, leaving us with x times x plus 12 equals 76. Then we just multiply out the left side using the distributive property, giving us that same result of x squared plus 12x equals 76. Now, we're ready to complete the square. Pause the video and finish solving this equation by yourself. Then we'll check your work. We build our square by splitting that 12x in half, which reveals a side length of x plus 6. Multiplying 6 times 6 shows that our empty right bottom box needs to have a 36 in it. So we add 36 to both sides. Using our model, we can rewrite the equation as x plus 6 squared equals 112. Now we take the square root of both sides. We can simplify the square root of 112 since it can be broken down into square root of 16 times the square root of 7, and the square root of 16 is 4. Finally, we subtract 6 from both sides. Our solutions are x equals negative 6 plus or minus 4 times the square root of 7. In this lesson, we solved equations that started off looking very differently, but with some algebraic work, we were able to get them ready for completing the square. Remember also that some equations we solved already had the square completed for us. So a good first step is to ask yourself, is completing the square actually needed? Such as it is in x squared minus 5x plus 3 equals 4? Or perhaps the x is already in a square, like it is in x minus 5 squared plus 3 equals 4. In cases like that, there is no need for completing the square, and just using inverse operations is often enough to solve the whole equation. Another good note to have in mind is that equations in the form x squared plus bx equals c are often simpler for completing the square. For example, if we have the equation 4x squared plus 12x minus 20 equals 0, we could first divide both sides by 4 and then add 5 on both sides. Now it's in a great form to start completing the square. And there you go. You now have all the necessary tools to solve any quadratic equation, no matter what form you have it in at the start. Once you've finished up your guided notes, check out the additional practice in your PDF. And after that, all that's left is the online practice. Good luck with that, and I'll see you next time.
Hey.